Hi everybody, I'm Dr. Biomed. Welcome to the Biomed Cafe channel. In this channel, complex biological and medical contents are presented in a simple, classified, and summarized form. Also, I have designed a quiz game for you. I will explain about the quiz game in the end of this video. The topic of this video is microtubules. Please subscribe to this channel, and if you like the contents of this video, please like it. Cytoskeleton. The cytoskeleton is a network of filaments and tubules. It extends throughout the cell to the cytoplasm. It's located in all cells. It plays a role in giving shape to the cell, especially in cells without cell walls such as animal cells, in movement of cells and organelles, in organizing of cells, and in keeping the cell's organelles in their place. Cytoskeleton can be divided into three subgroups: microtubules, microfilaments, and intermediate filaments. Microtubules characteristics. They are the largest of the cytoskeleton fibers, despite the micro in their name. They are long hollow tubes. Their diameter is 23 to 25 nanometer. Their length is 50 micrometers. Their width is 23 to 27 nanometer, and their inner diameter is 11 to 15 nanometer. Microtubules are constantly growing or assembling and shrink or disassembling via the addition and removal of dimers. Microtubules structure. The most common form of a microtubule, comprising 13 protofilaments in a tubular arrangement. Organization. Alpha-tubulin and beta-tubulin join together and form a tubulin dimer. Tubulin dimer join together and form a protofilament. About 13 protofilaments make microtubule. They are commonly organized by a centrosome. Alpha-tubulin and beta-tubulin. They are approximately 50% identical at the amino acid level. They bind to GTP for polymerization. Their molecular weight is approximately 50 kilodalton. Protofilament. They are polar molecules. It means they have positive and negative ends. The positive end has beta subunit, and the negative end has alpha subunit. Centrosome. It's a microtubule organizing center, or MTOC, of the cell during mitosis. In animal cells, microtubules radiate outwards from an organelle in the centrosome. In plant and fungi cells, there are not centrosomes. Instead, they have the nuclear envelope. Centrosomes have two cylinders in their structure. They're called centrioles. Centrioles have oriented at right angles to each other. The centriole is formed from 9 main microtubules. Their length is approximately 400 nanometers and their circumference is approximately 200 nanometers. Centrosomes play a role in maintaining the polarity of microtubules during mitosis because the minus ends of each microtubule begin at the centrosome, and the plus ends of each microtubule radiate out in all directions. Another function of centrosomes is helping to mitosis, because most microtubules involved in mitosis originate from the centrosome. Tip: most cells only have one centrosome. Right before mitosis, the centrosome duplicates and the cell contains 2 centrosomes. Microtubule organization can be divided into 2 steps: nucleation and polymerization. Nucleation. It's the events that initiate the formation of microtubules from the tubulin dimer. Locations for the nucleation in animal cells are the centrosome, that symmetrical nucleation occurs, and Golgi apparatus, that asymmetrical nucleation occurs. Locations for the nucleation in plant cells are basal bodies of cilia and flagella and the spindle pole bodies. Polymerization is following the initial nucleation events that tubulin monomers add to the growing polymer. It can occur at both the positive and negative ends. Positive end grows relatively fast, but negative ends grows relatively slow. Adding or removing monomers is equal to the ratio of alpha-beta tubulin dimer concentration to critical concentration. If alpha-beta tubulin dimer's concentration is greater than the critical concentration, the length of the microtubule will increase, or the microtubule will polymerize or grow or assemble. But if the alpha-beta tubulin dimer's concentration is less than the critical concentration, the length of the microtubule will decrease, or the microtubule depolymerize or shrink or disassemble. Dynamic instability. Microtubules have dynamic instability. At high free GTP tubulin dimer concentrations, rapid assembly at the positive end occurs. But when GTP hydrolyzes at the positive end, the tubulin dimer interaction weakens and rapid disassembly at the positive end occurs. Microtubules functions. 1. Cell movement. Structures like cilia and flagella are made of microtubules. Microtubules allow whole cells to move from one place to another by contracting at one end of the cell and expanding in another. 2. Cell division. Microtubules play a key role in forming the mitotic spindle that is formed during cell division in eukaryotic cells. Cell transport. Microtubules provide tracks for motor proteins called kinesins and dyneins, which transport vesicles and organelles inside a cell cytoplasm. 4. Maintaining the structure of the cell. Microtubules together with microfilaments and intermediate filaments form the cytoskeleton and maintaining the structure of the cell. 5. Cell migration. Microtubule plus ends are often localized to particular structures. This configuration helps to deliver microtubule-bound vesicles from the Golgi to the site of polarity. 6. Making cilia and flagella. Microtubules make up the internal structure of cilia and flagella. Development. Microtubules have essential role in development of the cytoskeleton and the nervous system. 8. Gene regulation. Microtubules can influence gene expression. For example, the relationship between the drug-mediated depolymerization of microtubules and the specific expression of transcription factors. Interacting proteins with microtubules can be divided into two groups: microtubule-associated proteins and motor proteins. Microtubule-associated proteins. They play a role in regulating of microtubule dynamics in vivo. They can be divided into 4 subgroups. The first subgroup is tau proteins. They directly bind microtubules. Their molecular weight is 55 to 62 kilodalton. They play a role in promoting nucleation, in preventing disassembly, in inducing formation of parallel arrays, and in stabilizing microtubules in axons. The second subgroup is plus-end tracking proteins, or plus TIPS. They bind to the tips of growing microtubules. They play a role in regulating microtubule dynamics. The third subgroup is MAPS. Their molecular weight is 200 to 1000 kilodalton. They can be divided into 4 subgroups: MAP1, MAP2, MAP3, and MAP4. MAP1. MAP1 has 3 subgroups: A, B, and C. C is cytoplasmic dynein, and it plays a role in transporting of vesicles. MAP2. It binds with other cytoskeletal filaments. It's located in dendrites and in body of neurons. It plays a role in determining different cytoskeletal forms of axons and dendrites. And map 4 is located in the majority of cells. It plays a role in stabilizing microtubules. The fourth subgroup is microtubule-serving proteins. They play a role in the stabilizing effect by cleaving and by inducing the polymerization of microtubule, and in regulating the number and length of microtubules via their destabilizing activities. They can be divided into three subgroups: catenin, spastin, and figestin. Motor proteins. Two important examples of motor proteins are kinesin and dynein. They utilize the energy from ATP hydrolysis. They play a role in vesicle trafficking and cell division. Microtubule can be divided into three subclasses: astral microtubules, interpolar microtubules, and kinetochore microtubules. Astral microtubules. They only exist during and around mitosis. They originate from the centrosome. They do not interact with the chromosomes, kinetochores, or microtubules originating from the other centrosome. They radiate from the empty OCS of the cell to the cell membrane. They play a role in keeping the mitotic spindle in place, in helping to cytokinesis, and in interacting with motor proteins at the cell membrane. Tip: without astral microtubules, the mitotic spindle can form, but its orientation in the cell is not always correct, and thus mitosis does not occur as effectively. Interpolar microtubules. They radiate out from the centrosome towards the mitotic spindle during mitosis. Between microtubules during mitosis, they are most abundant, 95%, and they are most dynamic. They do not attach to the kinetochores. Half-life of interpolar microtubules is less than 1 minute. They play a role in helping separate chromosomes. Kinetochore microtubules or car fiber. Kinetochore is a protein complex that helps attach chromosomes to microtubules in the mitotic spindle. Kinetochore microtubules form direct connection with the kinetochores in the mitotic spindle. Each chi fiber is equal to 20 to 40 parallel microtubules. They have attachments at one end to the centrosome and on the other to the kinetochore. Half-life of kinetochore microtubules is 4 to 8 minutes. They play a role in attaching to the chromosomes and helping to pull them apart. Thank you for watching. Please subscribe to this channel, and if you like the contents of this video, please like it. Now it's time for the quiz game. I have put the link to the quiz game in the description of this video. Download it for free and enjoy it. In the next video, I will talk about another biomedical topic in a simple, classified, and summarized form. Until the next video, bye!